Welcome back to today's Explainer. We are jumping right into a totally fascinating breakthrough today. We're looking at a space where artificial intelligence is literally learning to build memory exactly like a human brain. It's called HippoRAG, a neurobiologically inspired long-term memory system. So if you've ever found yourself wondering how we can finally get AI to stop forgetting things and actually start connecting the dots, you are in the right place. Let's dive in.
To really grasp why this is such a game changer, let's kick things off with a bit of detective work. Here's a seemingly simple question. Which Stanford professor works on the neuroscience of Alzheimer's? Now, if you know a bit about the field, your brain instantly goes to work, right? You take the clue Stanford, you link it up with the clue Alzheimer's neuroscience, and boom, you retrieve the answer. But here's the crazy part. Current AI, it hits a massive solid brick wall trying to figure out this exact type of query.
So why the struggle? Well, look at how standard AI operates. Modern AI uses something called retrieval augmented generation, or RAG, to look up facts. The problem is, standard RAG encodes text passages completely in isolation. It's like looking at puzzle pieces in separate locked rooms. If one document says Professor X is at Stanford, and a totally different document somewhere else says Professor X studies Alzheimer's, standard AI just can't easily connect them. Our human brains, though, we use associative memory. We seamlessly leap across completely disconnected memories to piece the puzzle together and solve the mystery. Okay, here's our roadmap for today. We're going to cover the AI memory problem, the human brain solution, meet HippoRAG, see how artificial memory is built, explore its pathfinding superpower, and finally, look at why it's smarter, faster, and cheaper. Section 1. The AI memory problem and the knowledge integration bottleneck. Look, standard RAG is perfectly fine if you ask it a direct question where the answer is neatly packaged in a single paragraph. But it completely falls apart when it has to integrate knowledge across different passages. To get around this, developers basically force AI to do these expensive, iterative, multi-step searches. It searches, reads, searches again, reads again, and even with all that extra compute power, it still fundamentally fails at what we call pathfinding multi-hop queries, basically whenever the clues are scattered.
Which brings us to Section 2, the human brain's solution, millions of years of evolution.
Our mammalian brains have had millions of years to perfect this. We can store vast amounts of knowledge and add to it without suddenly forgetting the old stuff. How? It all comes down to a crucial academic concept called the hippocampal memory indexing theory. Think of human long-term memory as a beautiful team effort. Your neocortex processes the actual, high-level representations of what you experience. Then, your hippocampus, that C-shaped structure in the brain, acts as the ultimate cross-referencing index. It doesn't hold the full memory. It holds a web of associations pointing back to the neocortex. So when you need to remember something, the hippocampus triggers the right associations and pulls the whole memory together for you.
Section 3, meet HippoRAG, the master detective.
This is where it gets incredibly cool. We're introducing a novel AI architecture designed directly, and I mean literally, from that biological blueprint we just talked about. Notice how the architecture on screen perfectly mirrors biology. The large language model itself acts as the artificial neocortex, processing the raw text. Then the researchers built an artificial hippocampus using a knowledge graph paired with a personalized PageRank algorithm. It is quite literally an artificial brain structure designed to keep distinct memories unique and to recall full memories from just a partial clue, exactly like we do.
Section 4. Building artificial memory, the two-phase pipeline.
So, how do you actually code an artificial hippocampus? It's a two-step dance. Step 1 is offline indexing, which is basically the AI encoding a memory, reading info and building its index. Step 2 is online retrieval, which equates to pattern completion. That's what happens the exact second a user asks a question, and the AI has to instantly pull the answer from that index.
Let's break down that first step, the offline indexing. The LLM processes text using something called Open Information Extraction, or OpenIE. It pulls out distinct noun phrases and maps the relationships between them. It takes raw paragraphs and turns them into this massive, interconnected, schemaless knowledge graph. It's literally building a web of associations, just like your brain linking a specific person to a specific place. Then we hit step 2, online retrieval. You ask a question, the AI extracts the key entities, and then it uses a personalized PageRank algorithm. Yeah, it's very similar to the math that built Google's original search engine. It sends probability signals flowing through the knowledge graph. By starting at the query nodes, the algorithm lights up the relevant neural pathways mathematically, allowing it to rank and retrieve the exact right documents.
Moving right along to Section 5, the pathfinding superpower, connecting the clues.
Okay, let's go back to our Stanford professor mystery. The crucial difference here is path following versus path finding. Standard AI is great at path following. If clue A links to B and B links to C, it can follow the trail. But finding our professor requires path finding because Stanford and Alzheimer's are disjointed clues. They might not appear together in any single document. Standard multi-step AI completely fails here. But HippoRAG, thanks to its biological design, it searches those disjointed clues and solves the mystery, identifying Professor Thomas Sudoff effortlessly in a single step.
I absolutely love how the researchers put it. They state, HippoRAG allows LLMs to build and leverage a similar graph of associations to tackle knowledge integration tasks. This architecture literally gives artificial intelligence the closest thing to a human aha moment. It's not just fetching files anymore, it is truly integrating knowledge.
Section 6. Smarter, faster, cheaper. The benchmark result.
Concepts are great, but let's talk data. Check out this number. Single-step retrieval with HippoRAG is 10 to 30 times cheaper than current state-of-the-art iterative multi-step methods because it navigates the graph mathematically instead of forcing a massive language model to read and reread documents. The computational cost just plummets.
And it doesn't stop at cost. It is also 6 to 13 times faster. Think about that for a second. Instead of waiting for the AI to do loop after loop of searching, HippoRAG fires off its algorithm and delivers the integrated answer at lightning speed. Now you might be wondering, does this speed sacrifice quality? Absolutely not. Looking at the benchmark data, HippoRAG actually outperforms top-tier methods like BM25 and Colbert V2. On highly complex multi-hop question answering benchmarks, we're seeing performance gains of up to 20%. It's just a fundamentally better way to retrieve complex information. So, let's bring it all home. Why does this actually matter for us? First, it solves complex knowledge integration in a single, super efficient step. Second, just like a real brain, it updates continually. You just add new nodes to the graph without forcing the AI to relearn everything from scratch. And finally, it's highly adaptable. It works incredibly well even with smaller open-source models like Llama 3, meaning developers everywhere can start using this biological blueprint today.
Which leaves us with this final, totally thrilling thought to ponder. We just witnessed an incredible leap in AI capability, unlocked entirely by studying the mammalian brain. If the key to unlocking this massive bottleneck in artificial intelligence was hidden inside our own minds all along, what other biological secrets are just waiting to be translated into code? Thank you so much for joining me for this explainer. Keep asking questions, and I'll see you next time.